When you get a new board from the fab, sometimes there are routing burrs or bumps along the edges of the board, like these. It's pretty easy to take these off with sandpaper or a sander. I'm wearing gloves to keep my hands clean. The edges of the circuit board should be flat and smooth like this. We'll start by soldering the small surface mount components first. Apply some flux to help the solder flow onto the contact points and transfer the heat. You may need to use some pins and tweezers to place the small parts, such as this Schottky diode array. You should tin or solder one pad first to act as an anchor point for a part. Solder the anchor point after aligning the part, then solder the outer legs. I like to refloat the joints to relieve possible stress. This 4.7 microfarad capacitor already had solder on its leads, so I don't have to tin the board pads. Sometimes a part will get hot enough that all of its solder points are molten. You should let off on the soldering to let it cool down a bit if this happens. This 0.1 microfarad capacitor also has solder already on its leads. These capacitors are in parallel, so while it's not desirable that they are adjacent like this won't cause any electrical problems. Here, I've tinned a single pad to act as an anchor point for this EEPROM chip. This chip should be oriented so that pin 1, indicated by a divot, should be close to the IC1 label. Once you've got the part aligned and anchored, go ahead and solder the other leads. You can distribute solder among the adjacent legs by running the soldering iron across all of them. Make sure there's no solder shorts between the chip legs. You can remove a small amount of solder by cleaning the soldering iron tip. For the RF surface mount components, we'll start by tinning anchor points on all the outer pads. Make sure the solder has actually flowed onto the part leads and make a solid connection. A concave surface of the solder is a good indicator. Remember that for soldering to work, both surfaces have to be hot enough for solder to melt on both of them. Next, solder these 86.6 ohm shunt resistors. followed by these 43.3 ohm series resistors. Once all of these parts are in place, solder the inner pads. Reflow the outer pads to ensure a good connection. Once that's all done, get a multimeter to measure resistance. We'll check to make sure there's about 130 ohms between the RF source and ground on each channel. The meter indicates about 125 ohms here because some imperfect parts were being used. These were later replaced with the correct ones that read about 130 ohms total. Testing the 43.3 ohm series resistors reveals no shorts. Testing the DC blocking capacitors reveals no passive direct current. We'll now begin soldering connectors, starting with the 0.1 inch pitch pin header. Like before, use an anchor point to fix it after aligning. Then solder the rest of the pins. You can see that my soldering iron is dirty. You can remove extra solder by using a flux-dipped copper braid called a solder wick. I'm going to give this board a clean with some IPA, or rubbing alcohol, and a horsehair brush before moving on to the other connectors. The IPA dissolves the flux, so you may have to rinse the board after scrubbing. Before we solder the SMA connectors, put flux where they'll go. I anchor SMA connectors with the signal pin because it's the easiest connections to heat up. Make sure there's just the right amount of solder to have a shallow concave surface of solder between the pin and the board trace. You may have to reflow previous solder to get the connector in place. You'll also need to let the solder solidify before letting go of the part. Sorry for the connector being sideways, I didn't see this until afterwards. Soldering the ground pins can be a bit tricky because it takes a lot of heat to bring their temperature up to the melting point of solder. You may need to set the soldering iron to 850 degrees Fahrenheit for these large pieces of metal. Flux can help transfer the heat a bit. To flow solder between the ground pins and the board, I tap the solder several times until I see it pulsating on the other side of the pin, like this. Let's go ahead and do the same to the other ground pins. Make sure you clean your soldering tip regularly, especially at higher temperatures. Let's do the same for the other side, starting with flux. Here, we'll make sure the pin header was soldered correctly by testing several combinations of possible shorts. This test shows no faults. This next test checks for ground shorts to the SMA signal pin. No ground shorts, solder worked, and DC blocking capacitors work. Great. Next, we need to solder on the DVI connector. It slips on fairly easily if no pins are bent. It shouldn't take a lot of force to snap in. Make sure all the pins are poking through to make sure none are bent. We'll start soldering by putting flux over all of the pins, then soldering the structural anchors. These large holes should be filled with solder but not overflowing. Then go around and give a little bit of solder to each of the pins. The ones attached to ground need special attention because they need more heat to warm up. All of them should have a shallow concave solder surface and should not bead up. After soldering all of them, go back and reflow them just to verify they have the right amount of solder and were soldered correctly. Fix any imperfections you find, and remember to keep your soldering iron tip clean. We'll install the 10-position ribbon cable header next. Make sure the key notch is facing outwards, like in the board marks. Keep the connector pressed in while you anchor one of its pins. You don't want the connector to be slightly raised off the board. Again, pins connecting to the ground plane will take more time to warm up. Anchor another pin on the opposite side of the connector. Make sure solder goes completely around the pins. Once we're all done soldering, we'll clean all of the flux off with more IP and scrubbing. Flux that has been burned a bit will take more scrubbing to get off. Make sure you rinse the board with IPA as you scrub to get everything off. We'll need to assemble the ribbon cable next. This 10-signal cable has one wire marked red to help with orientation. These clips slice through the plastic and make contact with the metal in the wires. Use ribbon cable pliers to clamp the assembly together. The surfaces of these pliers remain parallel to ensure equally distributed force. Once everything is in place, clamp it down. The upper plastic clip will lock into notches in the larger lower piece. This setup, however, is vulnerable to coming apart, so we'll install the strain relief clip like this. Take note of the direction the key tab is facing. Next, we'll install this ferrite ring to help prevent RF signals from traveling down this cable. Note how the marked wire is still on the same side. The orientation of the second connector needs to be the same as the first, with the key tab facing the same direction. Here, they are both on the left side. Once you're sure the orientation is correct, clamp it down and install the string lathe clip like before. This is just showing here that both key tabs have the same orientation.
To prevent possible shorts, put some heavy tape on the back and cut to size.
For large pieces of metal, such as ground planes or connectors, temporarily raise the temperature of the soldering iron to 850 degrees Fahrenheit. Don't leave it at this temperature for too long, as grimy oxidization will develop faster at higher temperatures. I like to hold soldering irons like this, so that if the cable gets snagged, it won't jerk the tip. A soldering iron needs cleaning when the tip is no longer shiny or has particles stuck to it. When oxidization builds up, stab it in a wire brush a few times to clean it off. A clean soldering tip will be shiny with a tin covering. When you're done soldering, clean the tip before turning the iron off.